talk about right triangle trig and how we use it in physics class. And so let's go ahead and get started. So the first thing we're going to talk about to introduce the right triangle trig is where it comes from, because I think that's useful information. If you already know this, you can skip this part. This might be review for you, and that's okay. Or maybe you never learned this, and this is all new, and that's okay too. Write as much as you want or as little as you want, but it's helpful to listen, okay? So we're going to start with the unit circle. The unit circle has a radius of 1. That's why it's called a unit circle, because it's got a radius of 1. And this is a drawing of it. There's the radius of 1. And what we're going to do is we're going to pick out what we call an arc length. So it looks like sort of a piece of pie. So it has a radius of 1, and we've traveled some angle, and that gives us this arc length over here. That's the S. The S is the arc length. And the arc length we can find by multiplying the radius times the angle. And that comes from, the circumference. So we're just looking at a piece of it. And so it's a proportion of that arc length there. We can look at that some other time if you really want to. And since the radius is 1, the S is equal to the arc length. So that's where we're going to be using that. And we're going to look at that S equals R theta a whole bunch next semester when we start talking about rotational motion. We'll get to that later, though. So let's talk about that theta right now. A whole lot right here in this sentence. It's a Greek letter. It's spelled theta. We call it theta. It's a lowercase theta. It means the angle, and we're always measuring it in physics from the x-axis, the positive x-axis, counterclockwise. So that goes the opposite direction of a clock. And right now we're measuring it in radians. We'll be able to measure it in degrees in a little bit. Sometime later, we're going to be measuring it in radians. If you take calculus-based physics, eventually you'll be measuring it in radians most of the time anyway. Right now, we're going to look at radians because that is useful information to do, okay? Whoops, wrong button. I'm trying to scroll. There we go. Too many fingers. Okay. So when we define the trig functions, we're going to be looking at the unit circle, and we're going to be moving that arc length theta through an amount of radians. We're going to go around the circle an amount t, an angle t to move it. Okay, and that's going to correspond to a point on the circle, the unit circle, the point P that has the coordinates a, b. Okay, and that coordinates a, b is going to be a distance of 1 from the origin. And that's going to look like this. Okay. Whoa, I erased too much. Hang on. There we go. Okay. So we've got our x and y axis there, and the point P is on the circle, and there's A and B, and the angle T that we've moved our radius around. Okay. So we've got the point P there. And so when we define our functions, we're going to be looking at the triangle A, B, and T, not T, but R, that makes there. And I've drawn that over here so that we can just look at it. You see where that comes from on the unit circle there. So R has a radius of 1. We've got this angle T over there. We've got a right angle down there on the bottom right corner. And then that other angle at the top we could also know too, right? Because the sum of those angles would be 180 degrees. And so what we're going to do is we're going to be defining our trig functions. So those trig functions, you've heard of them before, I'm sure, because you took geometry, although you might not remember it. Maybe you took it during the pandemic and you've completely forgotten everything. And that's okay. That happens. I forget stuff too. There's sine, cosine, and tangent. And so where these definitions come from is it's about these ratios of the circle. And it actually started out like what people did was they were looking for values on this unit circle, and they were actually measuring them, and they had charts. And it used to be that if you wanted to find the sine, cosine, and tangent, you had this giant book. I have one of these giant books if you want to look them up sometime. And so if you wanted to find the sine of an angle, you had to go look it up in a book. And so when the radius is 1, the sine of that angle t is b, and the sine of the angle, or the cosine of the angle t is a. And the tangent of the angle t is the ratio of b to a. And that's just how they're defined. And so people, even like thousands of years ago, I don't know actually how long ago they started doing this, they measured these things on a unit circle. And they wrote them down in big charts. And that's how they found the sine of the angle. Now you have a calculator that has access to that information. And so when you push the buttons on your calculator, it just looks that up for you. But now we can do this for any angle regardless of of whether it's measured in radians or degrees by pushing buttons on your calculator. And so as long as it's still a radius of 1, it would be the sine of the angle. Theta is b, the cosine of the angle is a, and the tangent of the angle is b over a. But what if you're not using a unit circle and you have instead a triangle that has some radius of whatever the heck you want it to be? Maybe it's smaller, maybe it's larger. Well, it would be some ratio, right? If I drew a bigger circle around this circle that I have here, I would have these similar triangles, right? In geometry, you played with similar triangles all the time, hopefully. If you didn't, then your geometry teacher failed you miserably. I'm so sorry. But it would just be for any angle, theta, and any r, you would just have that ratio of the r in there, okay? So it'd be b over r and a over r and b over a, but because the r's cancel out, so tangent still looks the same. But most students are used to seeing this in terms of the opposite side because b is the opposite of the angle, and adjacent side because a is right next to it, adjacent is next to, and then the hypotenuse because that radius is the longest side of the triangle, and so they're used to seeing it like this, opposite and adjacent, and so they've memorized also SOHCAHTOA, with those letters there, and that might be what you actually remember, and that's okay. That is a good mnemonic device to help you remember which ones are which for the formulas, and that might be necessary, okay? So the biggest thing that students do when they are using trig functions in physics class is they don't pay attention to what their calculator is set on when they're doing this. So your calculator has different modes that it can use to calculate sine, cosine, and tangent. Most of your angles in this class are going to be given in degrees, and so you need to make sure that your calculator is in degree mode. And what that looks like on a calculator screen is this. You can zoom in right there. This one is on, here, I think I can zoom in for you there. This is a TI-83 Plus. The TI-84 Plus has a similar looking screen. You get to this by going to mode. Sometimes there might be settings. I don't know what the newer calculators look like, but there's radians right here. Oh, so good for highlights, radians and degrees. And you definitely want to make sure that degrees is selected. On a plain old scientific calculator, it's just a button. There's like a rad and a deg button, and you need to make sure it says deg instead of rad when you're doing these calculations, okay? Now, the other thing, the flip side of this with the triangles that you're going to need to know how to do is to go back. What if you need R and you have A and B? Well, that's some good old Pythagorean theorem, right? A squared plus B squared equals C squared, or in this case, R squared, okay? And what if you need the angle? Okay, well, this is where it gets fun, right? Okay, so what we're going to do is we're going to be undoing the trig function, and that looks like this. It looks like we take this. It looks like a sign with a little -1 on it. That's what it looks like. It's kind of like an inverse function. Okay, inverse sine. What do they call it? It's not the arc. That's something else. But we're undoing it. Okay, and so there's an inverse cosine and an inverse tangent. And those are just buttons on your calculator. So I took a picture of some buttons on the calculator. This is also the TI-83, but it looks like this on the other ones too. So where the sine, cosine, and tangent buttons are, the sine, cosine, or inverse sine, inverse cosine, and inverse tangent are usually, you just have to hit the second key to get to those. So whichever one you might be using, depending on the information that you have to get the angle, those would be the buttons. And then you would just make sure that the information is in parentheses when you do it, okay? And so we'll look at that a couple of times. There'll be some practice, and if you need more practice, you can always make sure you let me know, okay? Okay, so here's our calculator. No, never mind, I just said. Okay, so let's look at some examples in physics. All right, so we usually have to find components of vectors. In physics, we've talked about what vectors are. So velocity, acceleration, forces, these are the things that we're going to have to find components of at some point in time. We'll even be adding vectors later on. But right now, we're just looking for the components. So here's an example. A ball is launched with a velocity of 42 meters per second at an angle of 30. That should say 30 degrees. Let me fix that for you really fast. In a color that you can, whoops, nope. Okay. This should say degrees. There we go. Okay. Above the horizontal. Find the x and y components. Okay. So a drawing is incredibly useful. If you have not been drawing pictures of what you're working on, then you are shortchanging yourself. And so I drew a picture, and it may not be accurate, but that's okay. Exaggerating the angle may help you figure out some things later on, so that's okay. Your angles don't have to be perfect. It's fine. So here's my 30-degree angle. It's fine if it's not right. And I drew 42 meters per second on the hypotenuse because that's what that is. And I need to find Vx and Vy. I put V because that's a velocity, and then Vx and Vy there. And so I wrote that that's what I'm looking for, and that's great. Now I'm looking for the x and y components, which means I'm looking for those, the A and the B side over here. But all of these formulas that we were just looking at, none of them say, well, some of them say A equals and B equals, but I have an R value, and these functions that I have right in this area with the R's and these right here that have the hypotenuse in them, they're not written with just the opposite or adjacent by themselves. So I took some time and I wrote those over here. And let's see if I can get it without erasing everything else. So there's the sine has the opposite in it, which is the Vy, and the cosine has the adjacent in it, which is the Vx. So I wrote those over here so I could have those to look at. So Vx is what we'll do first. So I took this this one here. This one right here. So the A equals h cosine theta is V cosine theta right there. 42 cosine 30 is what I plugged in because it was 42 for the V cosine of the angle, which is 30. And then I just plugged that into my calculator, and then I stuck my unit back on the answer. Okay, the cosine of 30 doesn't have any units, so it doesn't change the units on the 42. I could have left my 42 with the unit on it. That might have actually been pretty helpful to see where that comes from. And so that is my Vx component. So the length of this side of the triangle is 36.37. Okay. And then I'm going to do the same thing to my Vy, which is V sine of theta. That uses this one. Whoops, I erased instead of written. Did I put it back? Yeah, okay. So this right here is for this one and this one here. There we go. So 42 sine of 30 gives me 21. So the Vy is that 21 length. Now sine of 30 is exactly a number. In fact, it looks like it's 0.5. Because 42, half of 42 is 21. Some of them have exact numbers, which is really cool. You might have studied that in your geometry class, and maybe you didn't, and that's okay. So sometimes in physics, so that's an example. If you need to see more examples, ask your teacher. There's also plenty of practice in the practice assignment that I gave you. But always ask. It's always okay to ask, okay? So the next thing we might have to do is finding the resultant. So I talked up here about getting R and getting theta and what you would do there. And so this is what we do in physics. We call it finding the resultant. That's a fun word right there, resultant. Right now, it means finding the hypotenuse of the components, but later on, we'll be adding vectors, especially when we're adding forces, to find out what the resultant force is. That's a really big thing that we do, and you'll get really good at it, don't worry. And so we're going to be looking for the answer. That's what we call it. So we're going to do an example. And in this situation, we're just going to be finding the resultant vector whose horizontal and vertical components are, and there's some horizontal and vertical components. So our horizontal is 27 newtons and our vertical is -3. What does that mean? Well, that just means it's going down instead of up. So a drawing can help here too. And there's my very tiny drawing. There's 27 newtons to the right and 3 newtons down, and I put a question mark because I'm looking for the hypotenuse. So to find the magnitude, so the magnitude is the length of the hypotenuse. I'm going to be using good old Pythagorean Theorem. So F squared, I called it F because it's forces. F squared equals Fx plus Fx squared plus Fy squared. So I'm going to be square rooting all of that in order to find F. So that's what I did. And then I stuck the 27 squared plus the 3 squared. 27 squared plus 3 squared turns out it's 738. And then I took the square root of that to get 27.16. It's really not that much bigger than 27, is it? Because the 3 is just so small in comparison. And that's okay. It's a very long and skinny triangle. That's what that is. Now to find the angle, again, I'm looking for something that is none of those equations up there were solved for. So what I did was I took the one that has what I'm given. Always choose to use your givens whenever possible. I'm given the opposite and the adjacent. I could use my hypotenuse, but then I would be doing some rounding to do that. And I don't like to do that. So if I used a tangent, I don't have to use my hypotenuse. So I used tangent of theta. And then I solved for theta by taking the inverse tangent. So I'll be doing tangent minus 1 of the opposite over the adjacent. And so when I wrote that down, I stuck my numbers in. The opposite is the -3. So I put that on top and the 27 on the bottom. And when I plugged that in my calculator, it gave me -6.34 because I was in degree mode. Now, sometimes when you do these, you get strange numbers that don't seem reasonable. And that's because, and I'm going to try and draw you a picture here. Let me uncover this. Sometimes it gives you strange numbers because what it's doing is it's giving you like the opposite angle. And that happens with tangent when it's like, maybe like this. So maybe you're looking for this angle, but it gives you this one instead. Okay, and so when that happens, you may have to think, oh, that's not the angle I'm looking for. Actually, that's not a good example. Let me give you a better example. So let's say your vector goes like this, and you're looking for this angle. But the angle that it gives you is actually this one. And so you may have to think, okay, that's not the angle that clearly your vector is going the opposite direction, right? So you may have to add 180 degrees or subtract 180 degrees to get the actual angle that your vector is going, okay? So when you get an answer, pay attention to what that number is and make sure that it makes sense, okay? That's all that means. Okay, so that is a probably less quick than I intended it to be run through of how to find components of a vector and also find the resultant of a vector and some background on sine, cosine, and tangent. If you have any questions, make sure you ask your teacher. Thanks for watching.